it goes too quick. So, but however, I think this part maybe it's quite easy for most of you. So maybe it's okay. We go a little bit faster. For the later part, so we can, you see, especially if you ask questions, if we discuss, and then that will make things much easier. Yeah, because this part might be a little bit too easy. So let's continue, right? So therefore, instead of so we have introduced the discontinuity preserving is regularization. Normally, you see that essentially you call that term a regularization term. The last one is a fitting term. So the fitting term, yeah. So essentially, you see that like here, yeah. So mostly you see that this is yeah, mostly you call this a regularization term. This is a fitting term. So you regularize this term. The minimization of this term will make the image regular. Oscillatory is not regular. Yeah, even discontinuity is not regular. But you see here we want a discontinuity, so we just kill. So this is regularization, and this is a fitting term. So therefore, you see TV is a discontinuity preserving regularization. You can also use a higher order. Right? So therefore, you see that yeah. So here is a lot of comparison between the TV and the fourth order. So therefore, you see that here is especially the original image. We just plot the contours, and here you add the noise only to the second half. You plot the contour. So therefore, if you add a little noise, and then the level curve are somehow completely destroyed, the level curve is getting too oscillatory. And so therefore, if you use the second order, so there's somehow more image later, you see the level curves. If you use the fourth order, the level curves looks more natural. So this is the fourth order. Later, I have one image. Maybe let's go to that image even now. You see that here is another comparison. Here is the level curve of the Lena image by the total variation. You see that if you add a little noise, and the level curve will destroy it. If you use a TV, you see you recover the level curve somehow. But the level curve, you see that it's not so smooth. Here, if you use a fourth order, it's another fourth order. You can see the level curve are much more natural, much more smooth. Here is if you use a TV, so it's you kill all the oscillation, but if the higher order was even better. But in fact, this one was not by the fourth order there. This one by the elasticas. So we will try to come to elasticas later. Yeah. So we were talking about yeah, this image. So you add a half, and they remove the noise, and this is a lot of numerical comparison between the fourth order and the second order. Let's skip those things. Maybe we also skip, yeah. So therefore, the fourth order is in fact is related to another thing. So the fourth order PDE. So fourth order PDE, you see that if you solve a fourth order PDE, you can decouple it to solve two second order PDEs. Right. If you do that one, so you see that, so this is a standard technique for partial differential equation. You solve a higher order PD, you can introduce some auxiliary variables and reduce the order, but you solve two equations. You solve a fourth order PDE, you can introduce two auxiliary variables, you can solve two second order PD. If you do that one, there is a physical meaning. One of the physical meaning that one of the PD is not processing the partial differential equation, but processing the derivative. One of the PD will do that. If you do that one, so you see, why not just directly first process the derivative? So therefore, if this is an image, if this is a surface plot, and here you see, you can see the corresponding contour. And so therefore, you see that if this is non-zero gradient U divided by this one, this is, I write n. So what's the geometrical meaning of this n? This you should have learned in the calculus. What's the geometrical meaning of this n? Huh? Yeah, this is a unit normal derivative to the level curves. So this will be unit normal derivative to the level curve. So therefore, if you rotate it by 90 degrees, so here should be y, here should be y, here should be x. Yeah, so here there's a tempo, here should be y here. If you rotate it by 90 degrees, so this will be the tangent vectors. Those will be tangent vector to the level curve. So therefore, you see that to solve higher order PDE is somehow you first process those derivatives, and then you see recover the image from those derivatives. So why not do it directly? So therefore, you see that here is the true unit normals. If you just add a little noise, here will be the unit normal from the noise images. So here you can still see some kind of pattern. But once you add a little noise, you see nearly no pattern at all. No pattern at all. So therefore you see that you can still process, here's normal. But if you do a smoothing, and suddenly you get so good. Just do smooth the noisy vector, unit normal vectors, and this is what you get. And so that was just you smoothing this one, you get this one. And you see a lot of structure, but it was over smooth compared with the true normals. It was over smooth compared with the true normal. So here is the true normals. Here is a smooth one. You see that it's not the same, but looks quite, you see that somewhere it was over smoothed. You see, especially here. You see here, you see that it was over smooth. This part was well recovered. This part was well recovered. If you see more clearly, you see that corner is over smooth, but still you see that the smooth normals contain a lot of information. So therefore, one way is instead of directly you see process the image, you first process the normals, and then you see that once you get the normal, here is the normals, and you can try to recover image such that the image unit normals fit into this vector. That's another way to do fourth order processing. Do you capture what I'm saying? Instead of solving fourth order partial differential equation, so you first smooth the normals. So here is the noisy normals. You smooth it, you get this one. And then you try to find the image such that this image, the normal fit into this one. So that's another way to use a higher order partial differential equation. So mathematically, essentially you see that you solve two ways. So you first give an image U0, you calculate the noise unit normals, you smooth those noisy images so that here is the total variation of a vector. So we briefly talked about it, but we didn't go further. So instead of a smooth image, you smooth a vector. So similarly, so here is the total variation of the vector. Here you put this one. But this vector, you see that need to be a unit normal vector. You put this one as a constant. So this is the first part. That's what I showed in that image. You smooth the normal vectors. And after you smooth normal vectors, how do you recover image? So therefore you see that, and then I want to recover image. And so here, so this one will be the unit normal vector. If you recover image D, and those are unit vector. And then you will ask this one to be as close. N0 is a noisy one, and here is a smooth one. So you want to ask your new image and equal to this one as much as possible, right? This you can do by least square, but that will smear out things. So therefore, instead of doing least square, so you can do this kind of, even there are different ways. So you can do this one. So essentially, you see that here is a recovered n, and here is the unit normal of the image I'm going to recover. Assume they have the angle is alpha. Angle is alpha. And so therefore you can see that this term equal to what? That term is essentially equal to gradient D. Here is a minus gradient D inner product with n. So this is essentially equal to gradient D minus gradient D normal n cosine alpha, right? But however, this one we impose a unit vector, so that this is equal to 1. So therefore you take it out. So here is a gradient d. So here is 1 minus cosine alpha dx dy, right? So assuming you see that if you minimize this term, what's the meaning?
Minimize angle or minimize gradient?
Yeah, this is no. This one, this is not okay. So this is also minimized, and so essentially you have an effect to minimize this term. This term equal to 0 if alpha equal to 0 or 2 pi. You see that. So therefore, essentially trying to minimize to get this term equal to 0 is essentially trying to get alpha equal to 0. So which means that you try to, you see, this angle is matched as much as possible. So that's a second step. So once you recover n, you try to find the image such that this one is as close to n as possible. How do you do it? So that was essentially minimize this. So the first term is trying to get the angle of those two as close as possible. And here, because you see we have a noise image, we can also, you see, balance those two parts. So therefore, you see that. So if you do those two, so that was somehow equivalent to minimize. So first process the normal vector, and then and so this part we use essentially the method we use was in a paper due to Vesey and Osher. I think it was published in Sun Journal Numerical. We use that method to compute that part. The second part is essentially the TV. Especially the second part, I can't remember. I didn't write down the. So therefore, the second part, if you do the Euler-Lagrange equation, in fact, this is what you get. So you do the Euler-Lagrange equation, you get this one. Divergence d minus n plus lambda, so d minus d0 equal to 0. So therefore, you see that the difference with the ROF model is that here we have if you take n equal to 0, this is essentially ROF model, right? So what is more ROF? You see that is, so the ROF model was essentially trying to match this one to a 0 vector. But here you see we put the n here. So you can see that this will be definitely better than the ROF, but however, you should preserve the discontinuity. I shouldn't say, you see, this is the best method, but you see that if you really want to get the image which is much better, and this is the direction where you can go. You see the ROF could be the starting point. You see that here you just put you have an estimation of the directions if you do this one, so it will make it better. Yeah. So this is essentially, you see that instead of directly processing the function, you could always process the derivatives, and once you get the derivatives, and then you recover the function, right? So you can even go higher. You see that instead of the derivative, you see recover the curvature. From curvature, you recover the derivative, and then from the derivative, recover the function. I think this for some application will be definitely better, right? So let's skip those ones. Yeah. So therefore, after the total variation and higher order derivatives, so I think the Mumford-Shah model is one of the mostly talked and used. And for image processing, and this one, so therefore you see I will talk more in the second part. We mostly use it for image segmentation. We'll talk more in the second part. So therefore you see we will not talk about here. So later we'll talk much more about the Mumford-Shah and how to use it for segmentation, right? There's another thing is the so-called elasticas. So this one I think is very difficult to compute, but nowadays you see you can compute very, very quickly, very quick. So the elasticas is essentially for 2D curve. For the 2D curve, assuming K is a curvature. So curvature measures how quickly a curve is turning, right? If you have a straight line, the curvature is 0. You have a circle, you have a constant curvature. So therefore, if an arbitrary curve, if the curvature is big there, that means you have a turning very, very sharply. If the curvature is low, you see the curve essentially goes in a constant direction. It doesn't turn. So therefore, you see that essentially this is measuring the bending energy of a curve. And so therefore, if B equal to 0, so this is essentially the length times the constant A. If E equal to 0, and this is just a measure is a bending energy. So therefore, the elasticous energy for a given curve is that you combine those two. You combine those two. So therefore, you see that elasticous has a lot of applications for mechanics. If you go to mechanical engineering, so there's a lot of simulation for elasticous. But for image processing, is essentially you see that assume I give a function u which is a represent image. And then you see that if you cut the function, you get a lot of level curves. You see here, for every given tau is one level curve. You give another tau, you get another level curve. So therefore, when tau varies, you get a lot of different level curves. And so therefore, you see that this will be the elasticous for one level curve. Right. So this measures this will be elastic of one level curve, and then you see here for a given tau, if you integrate with the tau, so this will be the total elasticous. It's not one level curve. You see elastic for all level curves. So therefore, you see that what kind of curve the elasticous will be high. For what kind of curve you get very high elasticous? Oscillatory curve, you get very high elasticity. But even you see that if you take B equal to 0, so therefore you see that these kind of oscillatory curves, you see you have this well-known curve. You see that you just add a triangle here, add a triangle here, add a triangle here. You see that for this one, you see the length is still bounded, but the elasticity will go to very, very high. So sometimes only regular length is not enough. You see oscillatory curve can have a small length, but you see once adding this bending energy, you will get a curve even much more regular. So you not only minimize the length, but also you minimize. You see how the curve is turning and bending. And so this is one curve integrated with all the tau, so that will give the total elasticus of an image. So therefore, we use it for image processing. And so therefore, you see that for the level curve of a given function, the curvature is essentially equal to this one. If the function is a smooth, and there is nowhere the gradient equal to 0. And this is the curvature of the level curves. And do you know how to calculate this one? Why this is correct? So it's some fundamental calculations. So you can parameterize the curve by x, s, y, s. You calculate the curvature, and they use an implicit function, right? You can. So the curvature of the level curves is equal to this one. And then you see either you can use this formula or use a co-area formula. So therefore, the co-area formula for 2D functions was essentially a function is that so you get so I have a co-area formula somewhere there. So this is the so-called code area formula. So therefore, omega, if you just use Wikipedia over the internet, you get the code area formula. So here is the dx, and this is for arbitrary gx, and this is equal to minus infinity, positive infinity. So here is all the level curves, u equal to tau. So here is a g, x. So this is a right. So this is a so-called code area formula. If you integration this one, and that was the integration of this one with the arc length. So here is with the arc length. So you integrate over the arc length for all the time levels, and then integrate the level, you integrate, and this is equal to this one. If you do this one, so therefore you see that, and this one, in fact, I got it from Wikipedia. You just Google search Wikipedia code area formula, you will get this one. You'll get this one. So therefore, if you use a code area formula, and then just use this one, so essentially you put this one as a G. You put this one as a G, and use this formula, and so therefore this is essentially, this becomes the total elasticus of all the level curves. So you integrate the elasticus of all the different level curves. So therefore you see that if a b equal to 0, this reduces to the TV, the total variation. And also this is it shows that the minimize the TV is minimize the sum of the length of all the level curves, right? Because the total variation is essentially, you see that, right? If so this is if you take a b equal to 0, so this is you see that you just calculate the length of all the level curves and then integrate with all the levels. So therefore, minimize the TV is essentially minimize the total length of all the level curves. Instead of just minimize the total length, you can minimize the total elasticus of all the level curves, and this will be total elasticus. So instead of using TV as a regularization term, so therefore you see that you can use a total elasticus instead of minimizing the TV. You minimize the total elasticus. So therefore give an image. So here is a u. So u is a given gamma. So therefore, if you do this one, so therefore this will be another way to regularize the image. Right, regularize the image. Essentially, you see that here are two questions. So what kind of a PDE we will get? Can we get any hint of what kind of PDE we will get? You see, you minimize this one. It's not solving this one. So you do minimize. So which means that you need a variation. You need to do variation on this term. You need to variation. You see, even this is a product. So can you give any hint? I think, yeah. Can you give any hint of what kind of PDE we should get? Right. So, sorry? Nonlinear, yeah, fourth order. So therefore, if a b equal to 0, so your variation of this one, you see that mostly your variation, the derivative, you get second order PDE due to the integration by part. But here you see you have a divergence. Here is a gradient dot. There's a divergence. You have a gradient. So therefore, if you put this one, you will get second order derivative mixed with the first order derivative. If you do variation, so the fourth order should come from this one. It's a very, very complicated fourth order. I think the elasticus, to introduce elastic for image processing, I think it can trace back by the very old paper by Mumford with two collaborators. I think later, and the French people, what was the name, Musso? They use Elasticas for inpainting. So I think they was really made popular by Tony Chang, Sung-Hwa Kang is a Korean, Sung-Hwa Kang and Jackie Shen. I think their paper was really the crucial paper to make the Elasticas popular for image processing. But they have used it for image inpainting. But in fact, you can use it for denoising, inpainting, zooming. There's no way just to use it for inpainting. So that's the reason you see we put the gamma here. So we put the gamma here for different applications. You just use a different gamma. I think maybe even I have a slide in the next part. So for example, for denoising, which means U0 is given for on gamma. For denoising, you see that the noisy image is given everywhere. So therefore, you see just take omega equal to gamma. So then if you choose the A and B properly, so this will remove the noise. And then the noise image, not only the level curve have you minimize the length, but you also minimize with the curvature. So therefore, this will be for denoising. And for inpainting, so for inpainting mostly is that you have an image. So therefore, you see this part, the missing, and here is a gamma. In the gamma part, so therefore, this is the image is known. The image is known. So therefore, the Elasticas, you see that you have a level curve outside. So those are the curves, the level contours outside the image. You want to connect the level curve. You see the same level, you want to connect them. When you connect the curve, so you not only want the length to be minimized, you also want the curvature to be minimized. That's the reason you minimize these Elasticas. So essentially you minimize, so the total Elasticas, A plus B, divergence, square, and this one. And then mostly choose a small epsilon, and then gamma U minus U0. So therefore you see that this is the total Elasticas. Mostly you see that was an Elastica in this region, Is this clear? So especially you see that when epsilon goes to 0, that was essentially you don't solve anything in the gamma region. You just use these boundary conditions here. You solve the Elasticas in this region, which minimize the Elasticas. And so therefore you can also use it for zooming. I think most probably. So therefore for image zooming, so essentially you see you have an image. And so therefore it's very coarse. And so therefore you have a pixel value here. Assuming you want to zoom it 3 times bigger. And then you see that you need to insert 2 here. Right? So therefore there's, you see all those points, you can do linear interpolation, bicubic interpolation, anything, right? But all those methods would have some kind of disadvantage. So to minimize the Elasticas, so essentially the gamma equal to the cos pixels. So you see that, and then the gamma equal to the cos pixel, U is only in the cos pixel. And you try to recover a new image, which has, you see the total Elasticas should be minimized, but on those cos grid, you should equal to the original value as much as possible. So this you could use this one as a zooming. You could use this one as a zooming, right? So therefore, you see conceptually this is 1 step higher than the TV, right? So you not only control the level curves, but you also control the curvature of the level curves. So therefore, TV you see mostly you see the length is minimized, but the curve doesn't look so natural. But mostly if you use the Elasticas, the curve looks more natural. So conceptually, this is one order higher. But the problem is see that this equation is how to solve it. The problem is you see that this equation is very complicated. Even you see that I think in the paper by Chang, Kang, Shen, there's a derivation about Euler-Lagrange equation. I can't do it by myself. To find that Euler-Lagrange equation for this term, I can't manage. It was very, very complicated, very, very complicated. There's another thing that computationally is very, very costly because of fourth order Pde, so therefore you must use a very, very small time step. You must use a very, very small time step. So therefore for ROF, mostly if you use explicit time marching, it takes about a few thousand steps. But for this one, if you use explicit time marching, mostly it takes more million steps. So it's only not a few thousand, it's really millions of time steps. But that's a past. That's a past. There are new methods which can really solve this one very, very quickly. We have a paper using Order-Lagrange, which you can solve it very, very, very quickly. Number of seconds you can solve it. So therefore, you see, solving of this equation is not a problem. It's not a problem anymore. So yeah, so the original plan was for the Mumford Shah, I will talk quite a lot in the second part. For the first numerical scheme, so I was thinking to talk about two methods. One is called the AOS, so which is the additive operator splitting scheme, and then I will then talk about Order-Lagrange. So there were a number of other methods, so therefore we don't have time to talk about all of them, so I will pick out the AOS and the Order-Lagrange. Mostly we will do that maybe by tomorrow. So and then we finish those things and then we go to the second part. The AOS is called additive operator splitting scheme, and the Order-Lagrange is something. This is really due to the split Bregman. So split Bregman by Stanley Osher and Tom Goulston. So that turns out to be one of the quickest methods for ROF. But later you see people found out, you see the split Bregman is just Order-Lagrange. But the Order, so if you can, the split Bregman you can use it for ROF. But if you really use the formulated Order-Lagrange, and you can use it for a large number of problems, include the Euler's elasticas. Also numerically it turns out very, very fast. Most of if you use Order-Lagrange, mostly turns out very, very fast. I think that was, I intend to talk this one. Maybe you see also I quickly show you what I plan to talk about the second part. So this is what I plan to talk about the second part. That one maybe most probably we start from next Monday. So I will talk about graph cards and bit minimization for image processing. So essentially I will concentrate on on segmentation, introduce the older methods. You see what are the elementary models, and then I will talk about level set methods, and this is still for many of you the transverse model. The transverse model. You see the piecewise constant things. And then the phase field things. And especially the convex relaxation, that was the convex relaxation things, which turns out very fast, very stable, combined with Order-Lagrange. And then I talk about graph card. So this one I will point out a number of relationships, and then the multi-phase transverse. You see also the even more phases. So using continuous card or different things. I think this part is quite exciting. So therefore, that was the next part of the lecture. Next part of the lecture. All right. So that was. So maybe today we just finish here. So tomorrow we go through in somehow quite detail. Go through those fast algorithms. Okay. Thank you for coming to the lecture.